Hi, my name is Caitlin McNamara, and this is my last and final video for our class. I will actually be discussing some previous research that I did back in 2008 when I was a high school student. This project continued from the time that I was in high school up through my sophomore year, and it resulted in a paper published in the Journal of Neurotrauma. So let's get started. So the title of my presentation is actually the title of the paper that I published with Dr. Jonathan Lifshitz at the Spinal Cord and Brain Injury Research Center. This was a presentation that I gave back last year at the National Conference for Undergraduate Research in Utah. I have modified the presentation a little bit just for time's sake. But the title, of course, is The Whisker Nuisance Task Identifies a Late Onset Persistent Sensory Sensitivity in Diffuse Brain Injured Rats, which is quite a mouthful, so I'm going to go ahead and explain what all of that means. So if you're interested, though, if you'd like to find the abstract, simply go to PubMed and type in Whisker Nuisance Task, and you can pull up the paper. It is free to view the entire, or you can even print the entire publication. So if you're interested, I recommend that you go and look up this journal article. So let's get started. Why should we care? First of all, what is traumatic brain injury, and what do I mean by diffuse traumatic brain injury? So if you think about traumatic brain injury, you may think of concussions, you may think of sports injuries, you may think of getting hit on the head in general. The difference between diffuse and focal injury in this case, focal injury being one area of the brain that is damaged, typically by, like, let's say, a bullet or something that goes straight in. It hurts one area of the brain and damages just that area. The problem with diffuse traumatic brain injury is that it causes, as the name suggests, problems throughout the brain. So we're talking about injury that occurs at the neuronal level where the axons and dendrites are separated. Think of silly putty, and if you stretch silly putty out and then you snap it, imagine that being a neuron and it just snapping in half. So imagine that, but all over the brain, and that is diffuse traumatic brain injury. And that occurs in estimated 1.7 million people annually, although this number is slightly old. The statistic is slightly old, so it could even be more than that today. And it is about a third of all injury-related deaths in the United States. So we're talking about a major problem here in the United States. Think about your sports injuries, your football, your wrestling, and all those times that you saw someone get a concussion or get knocked out. That was a form of mild diffuse traumatic brain injury. So about 75% of those TBIs, or what traumatic brain injuries, that occur each year are then those concussions that you see maybe on TV or in a YouTube video. Again, all of these statistics were reported by the Center for Disease Control, and again, as I mentioned before, they are the statistics are a little bit out of date. This was published back in 2010, so the numbers could have changed since then. So I'm going to explain a little bit more. As I was talking about, your football injuries, your wrestling, and you see several pictures on this slide where, someone getting punched in the face where they get knocked out, someone in a car wreck, or someone getting tackled. Nathan Stiles, the picture down in the lower left-hand corner, he was a football player, a high school football player who got severe concussion and ended up dying from the brain injury itself. So these are the different types of, or different areas that you could actually receive a brain injury. But the way that the diffuse brain injury works, if you look at the center image, is that imagine a car. If you're in a car and you're in a car wreck and you slam on your brakes and you are thrown forward. So imagine your brain sliding forward and getting damaged, and then it is snapped back as your body is thrown backward. So in that time, your brain is injured as it's stretched forward and then snapped back. Okay, so similar things happen when you get a concussion if you receive blunt force trauma, such as in a tackle, or as in wrestling, or here also in hockey, as you see them punching each other. But another area that we have focused on in past research is also in diffuse traumatic brain injury from soldiers that are returning from Iraq and Afghanistan, which represents the upper right-hand picture. So lots of different possible areas for traumatic brain injury research, and really it is a prevalent and widespread issue that should be addressed and has been addressed recently. In the NFL, you look over to the left in the picture of the Saints. The NFL recently got onto them about paying off their players for tackles where they injured the player, the opposing player. So you see that the NFL and colleges are trying to crack down on these tackles and this contact injury to help prevent TBI. So that's where that comes from. So this is just an interesting visualization of the number of injuries due to traumatic brain injury. So if you look at it as a pyramid, we have 52,000 people that die annually, roughly, from TBI, from traumatic brain injury. And again, these numbers are slightly out of date. But then if you look at the bottom, you see people that get a concussion or a mild traumatic brain injury, and they think that they feel okay, or they don't seem to have any issues up front with the injury, and so they seek no medical care. So those question marks refer to the people that, we are unable to measure and don't know how many receive those injuries annually, that could have suffered traumatic brain injury, but assume that they're okay and go about their daily life. The problem with that is that many people experience what we call morbidities due to their concussion or their mild traumatic brain injury, which can result in cognitive deficits, changes in mood, problems with problem solving. So those are just a few examples of the morbidities that can occur as a result of concussion. So again, diffuse traumatic brain injury, concussions, they are not something to be taken lightly. So when we talk about diffuse traumatic brain injury, as I said before, it's also called diffuse axonal injury, but it can encompass many regions of the brain. And what I mean by that is that, as I said before, for instance, in the car wreck example, if your entire brain is thrown forward and then snapped back, that entire brain area is affected. So again, the rapid acceleration, deceleration of the brain. Imagine again taking that silly putty as a neuron, stretching it out, and then rapid acceleration, stretch, and then snapping it in the deceleration. And you see that the neuron, or the silly putty neuron, snaps. And that's essentially what happens. And so then you get atrophy of the axons and the dendrites, and they atrophy or die. So those that do survive, though, because now there's all this deficit, there's the dying and the atrophying axons, the other neurons that have survived must rewire in some way, so they try to reconnect. And what we have hypothesized is that reconnection, that rewiring, is maladaptive, and that is why you see the morbidities that occur post-traumatic injury. So essentially that the concussion causes those axons to rupture, to atrophy, to die, and so the other neurons surrounding that dead axon, that dead dendrite, try to rewire, and as a result cause maladaptive rewiring, thus resulting in morbidities. So again, as I had discussed before, what are post-traumatic morbidities? Typically when you think of morbid, you think of death, but in this case we're talking about deficit. We're talking about pathological issues, psychological issues, deficits that occur, or impairments that occur as a result of disruption in brain circuitry and function. So what can they include? We discussed before post-concussion symptoms, issues with sensory processing, so the feeling of hot or cold may change, perhaps you're not able to perceive certain things as well as you did before, whether that's sight or hearing or taste, touch. And then there's also the behavioral and mental health problems. So if you think in the case of soldiers that are coming back from Afghanistan and Iraq, it's entirely possible that they're suffering from post-traumatic stress disorder. However, it's also possible that if they received a mild traumatic brain injury or a moderate traumatic brain injury, that part of that behavioral or mental change is due to that maladaptive rewiring. So we don't want to completely negate the fact that it could be psychological, but it also could be physiological. So essentially, and I'm going to give a little bit of a backstory on this experiment, Dr. Lifshitz noticed that in rats who had sustained a traumatic brain injury, that they did not or were aggravated by whisker stimulation, whereas sham animals or animals that did not receive brain injury, or even naive animals who didn't even have a surgery, actually enjoyed whisker stimulation. So he saw the stimulation of the whiskers as a way to detect or a way to identify these morbidities that can occur post-injury. So before, where we were unsure that morbidities even were the result of the TBI, he recognized that this manipulation of the rat whiskers could be a sign of the morbidities that occur post-traumatic injury. So we wanted to develop a task, or develop a neurobehavioral task, something that we could observe in order to rate the animals and detect whether they had morbidities or not. And if they had morbidities, it's most likely that we could predict whether they had an injury or not. So rats, as we know or may not know, rely heavily on their whiskers for sensory perception. So where we use our hands and our eyes to see the world around us, rats have actually very poor vision and really don't rely on their paws as much, but they rely very heavily on their whiskers to be able to detect the environment around them. So we thought that this would be a good area to manipulate in order to understand better what sensory deficits can occur as a result of traumatic brain injury. So the area that we focused on or wanted to look at in the brain was the whisker barrel circuit, and that's where we hypothesized the maladaptive rewiring was going on. And so we designed our product around creating groups of rats that had mild injury, moderate injury, and then some animals who received no injury, which we indicated as sham. So again, this picture indicates the circuitry that we thought was associated with sensory perception through the whiskers. The S1BF is the barrel field, or the whisker barrel field, and as you can see, through the traumatic brain injury, we believed that there was some sort of misconnection to the whisker barrel field. So that's just sort of the hypothesized problem that we saw and what we thought was going on. So how did we actually induce a brain injury? And the picture below looks quite archaic. However, this is actually what we used in order to induce traumatic brain injury. So essentially, the rats, if you can imagine a surgery table, and the rats are on their stomach with their head or skull exposed. They're under anesthetic, and we expose their skull area. We trephine, or we bore a hole into the top of their skull near their sutures, near the cranial sutures, and we bore a hole there and expose the dura mater. Now we don't want to trephine through the dura mater because then the whole experiment, that animal is unable to be used. So we have to be very careful when we trephine through the skull because it's very thin, and we have to make sure to preserve the dura mater. After that, we place a dental cap, so a plastic cap, and we use dental cement to hold that in, so it almost looks like the rat has a helmet on. And then we allow the rat to come to wake up, and then we check vital signs. We look to make sure that the rat's doing okay. And then we put the rat back under anesthetic for a few minutes, and we attach them to this machine So if you look at the lower right hand corner, this is our FPI, Fluid Percussion Injury Machine. Okay, so what you would do is you attach the rat to the valve there on the left. It's very small, you can barely see it, but you attach the rat there, and essentially what it's attached to is a fluid-filled cylinder right there in the middle. And then what you see is a pendulum, or we called it a hammer, but a pendulum. And we would raise that pendulum a certain degree, so we would draw what was called a death line, that beyond that line the rat was ensured not to survive the injury. And we would, based on the study of the actual brain itself and after, we decided what a moderate and mild injury was. So moderate typically was about 1 atmosphere of pressure, whereas a mild was typically 0.5 to 0.9 atmospheric pressure. So the raising of the pendulum would indicate how many atmospheres of pressure the rat would receive. So we release the pendulum, it swings down and hits the fluid-filled cylinder, and the fluid then causes that pressure against the brain, causing that, again, that rapid acceleration and deceleration of the brain. So we simulated then a diffuse traumatic brain injury. So then we would give the animals about a week to recover from the actual injury, and again, of course, prior to the injury we would test the animals of the whisker nuisance task, give them the injury, and then we would place them in an open field like we'd done before, and we would continue the whisker nuisance task and record the behavioral traits that we noticed or any changes that we noticed. And then once we had actually characterized the behaviors that we noticed that had changed, we basically made a sheet of various behaviors. So anything from freezing, which is maladaptive. Rats typically like to explore their environment. So if they freeze in the open field during the stimulation, we know that that is an adverse reaction to the stimulation. So we noted that. We noted their breathing, were they breathing rapidly or normally. We noted if they vocalized or if they tried to bite, or if they appeared aggressive towards the stimulation. So again, showing vocalizing, biting, or if they cowered, which would be, again, the freezing response. And so we rated that. A 0 on the scale would be a normal behavior, so not freezing, exploring the environment, not biting, not showing aggressive behavior, breathing normally, all the way to a 2, which would be adverse. So again, if you're thinking about, okay, does this animal have, a traumatic brain injury or not, what you would think of is typically an animal, or what we were thinking might happen is that an animal that had the traumatic brain injury would show more morbidities, would show a greater adversity or adverse response to the stimulation, therefore they would receive a higher score. More 2s, more 1s. Whereas animals that were naive or sham would receive a very low score. So that's what we kind of hypothesize, or how we would tell. And then based on those scores, we kind of try to see whether we were right or wrong. So, of course, I was the one that did. I didn't do the injuries, but I did do all the behavioral tasks. And of course, I was blinded to what injury they had received to ensure that that my own bias would not enter into the situation. So again, here's that sheet that I was talking about. So you see we have the behavioral criteria, and this took a really long time to put together because, of course, we had to spend a lot of time with the rats and characterizing what was normal versus what was not normal for rats. So again, you're looking at freezing, and what I mean by freezing is that they're defensive, they're not moving, they're cowering, fearful, whereas not freezing would be walking around, curious, they use their whiskers quite a bit, they're moving their whiskers about, and typically if they're in a frozen position, if you will, they retract their whiskers towards their body to protect themselves. So again, looking at the breathing, looking at, when we talk about whisking response, again, we're looking at the movement of the whiskers. Evading the stimulation, so are they trying to get away from the stick that we're using to manipulate their whiskers? If we presented the stick to them, do they bite it, or are they curious of it? Are they aggressive? Are they not aggressive? And then are they grooming? So if they're not grooming, we took that to be a normal reaction, but if they look to be irritated, as if they were like pulling on their whiskers or pulling on their hair, it could be a sign of irritation to the stimulation. So you see where a 0 is a normal reaction and a 2 is an adverse reaction. So what we hypothesize is that animals that had a higher score were more likely then to have had traumatic brain injury, whereas animals that had a lower score were more likely to not have had a traumatic brain injury. So here are our results. And what did we find? Essentially, you can see that the sham animals, and again, what I mean by sham is that we essentially opened up and exposed the skull, but we did not do an injury, okay? And you see that their scores were roughly about a 4. We did have high error there, but if you just look at the bars, roughly about a 4. And then you look at animals at 7 days, 28 days, and 56-day post-fluid percussion injury. We see that at about 28 days was about the highest score, at about 10 or 12. And so what does this really mean? And what we found is that sham animals were ambivalent or soothed by whisker stimulation, whereas brain-injured rats showed aggravated responses at 1 week, which is the 7 days, which then became significant at 4 weeks, okay, so the 28-day response, and 8 weeks, which is then 56 days. So we actually did have significant values at 28 and 56 day, or if you want to look at it at 4 and 8 weeks. So what does that mean? Essentially that our whisker nuisance task was able to identify morbidities, and that those morbidities then were also associated with animals that were either had moderate or mild traumatic brain injury, or we were able to show that animals that were shams had actually very low scores, indicating that they were not exhibiting any morbidities. So then the next question was, okay, so if we have a behavioral task that can detect morbidities, is there any way that we could use that to measure measure the efficacy of a therapeutic intervention? What I mean by that is that, if we were to allow the rats to explore an enriched environment, if we, thus using their whiskers on a day-to-day basis in an area that had multiple different types of stimuli, if we desensitize them by whisking their whiskers over and over on a daily basis, would that help? Or if we shaved their whiskers after injury, thus not allowing any stimulation, would that help? And what we found was that neither enriched environment, nor shaved whiskers, nor desensitization via constant stimulation of the whiskers was efficacious in reducing morbidities. However, we did find that the task was able to identify mild traumatic brain injury, which is important because we were able to identify a difference between sham animals and mild fluid percussion injury animals, and also identify moderate injury. So you see there on the right, and I'll show you the data from the other studies. You see there on the right that graph shows you the sham animal in the blue square box, okay, and then animals with moderate injury there, and then to the right the mild fluid percussion injury. So we see that our task was still able to identify slight differences, which is good. So here's the other data. You can see that none were significant so essentially we did not find a therapeutic intervention based on the whisker nuisance task. We did not find a therapeutic intervention that mitigated these morbidities. So what are our conclusions? Essentially, the whisker nuisance task is sensitive enough to detect sham, mild, and moderate brain injured animals. sham being no brain injury. That morbidities were not mitigated by any therapeutic interventions that we tried, or and we have not tried any others since then. And then the Whisker-Nuisance task is then finally a promising tool to help in the detection of post-traumatic morbidities. Now, the extension of that is, how do we translate that to humans? And that's the next big question. What is an area of the brain, or what is a sensory modality that we could use, that we could exploit in order to detect whether a human may be suffering morbidities as the result of maladaptive rewiring after post-traumatic brain injury. So that's the next big question. So if you have any questions or ideas, please feel free to contact Dr. Cooper. He can give you my email address. Again, I highly recommend reading the journal article. It was published in 2010, my sophomore year, in the Journal of Neurotrauma. And that is the end of my show. My presentation. I hope you enjoyed it, and I hope I stimulated your interest in traumatic brain injury. I find it fascinating, and something that we really should be paying attention to. If you have any questions, again, let Dr. Cooper know, and I'm sure he could forward you to me. I hope you guys have a great rest of your year, and good luck on your finals.